Our first speaker this afternoon is Heikki from the Finnish Centre for Pensions, who's going to talk about modelling future pensions requirements for the Finnish population. Heikki, all yours.
Okay, so my topic is pension microsimulation model ELSI, and well, I try to keep the emphasis on this simulation side and talk on pensions as little as possible. And in the simulation side, I'm trying to talk about the more technical things, though I'm not going to present you any code whatsoever. Okay, so in the Finnish Centre for Pensions, we have been doing a long time these long-term pension projections, and we have a cell-based PTS model. And it is also implemented using Dyalog APL. So we have a long history using the tool there. And in fact, this is a very good model, and it's still in very active use. But it has some limitations. So because there isn't any individual modeling, so you can't get all the results that you might want to have. So if you want to ask what would be the distribution of the pensions, say after 50 years from now, then you couldn't tell anything. So that's where the need for more refined tools arises. And our solution for this question is to start a microsimulation project. And well, here I have some picture from the macro model. So it says how our pension expenditure will behave in the future in Finland. So there are some various assumptions on economic and demographic behavior, and then you will have several different curves. But this is not very essential. I just wanted to have some pictures here. So what is microsimulation? So basically, the idea is that you have lots of individuals, persons, or other microunits, and then you simulate those microunits, and then if you want to get some aggregate results, you sum over all these individuals. And besides these aggregate results, you can get more refined results on distributions. You can easily consider some subpopulations and stuff like this. And the branch of microsimulation we are using is dynamic simulation. So dynamic in the sense that there is the dynamics in time. So the people are aged there, and there are several life events that occur to the people there. Somebody dies, there will be new young people, they are working, they're retiring, they get new education and all these kind of things. And all this is simulated every year again. Okay, so I have to say something about our pension system. So it's partially funded earnings-related pension system. And what does it mean? So the pensions that the individuals will get when they retire, they depend on the earnings history during their whole career. And then there are lots of details I'm skipping, but well, finally they will get some pension. It may be old age pension, disability pension, part-time pension. There are some other options as well. But what is important for us is that the system is under a major reform. And, well, maybe tomorrow we will know how it's going to be after 2017, maybe later. But anyway, this year I'm sure we will know what's going to happen. So this is also one reason why I'm not going to the details, because it's going to change anyway. But because of this reform, they really, the decision makers really need more refined analysis on what's going to happen. Okay, so our model, it's a dynamic microsimulation model of the Finnish pension system, and it's based on register data. So we have basically register data of all the adult population of Finland. So it's roughly 4 million individuals there, and then we take 5% sample out of there, and then we simulate this sample like 70 years away from now. And, well, all these people get older, some of them die at some point, and then also new young people and new immigrants will be added to the sample every year. And what we simulate working careers, earnings for those who are working each year, and finally, when these people retire, we simulate some pensions for them. Okay, and what kind of results we are expecting? Pension distributions, replacement rates, some results on subpopulations. For example, if you want to have want to know what is the pension distribution of like university educated women in 2040, for example, then this kind of questions we can answer using our model. Okay, the model is as here. So I first draw this picture, so I only had these 5 boxes here, and then the arrows were flowing from top to the bottom, and I thought it's very like elegant and easily understandable. But then my colleague said that, okay, maybe you should add something, and then there appeared all these 7 other boxes here around. But I still think that the important part is here. So what do? First you have data, okay? Then you simulate every year what the people do. So who is working, who is unemployed, who will retire, who will die, who will, well, get new education, and who will emigrate, things like this. And after you know what the people are doing, for those who are working, I simulate some earnings. So based on their earnings history, I generate some new earnings for them. And after I have the earnings, then I can compute the earnings-related pension when they are retiring. And after all these steps, I get some results, and it depends on the questions that we have been asked, what kind of results we will have. Okay. And what this has to do with APL, so basically, well, each box is an APL workspace. So for my model structure, for example, this population model is one workspace, then this earnings module is another, and so on. And actually, all these external white blocks here, they are also some APL workspaces. And then these these ones are something that we are planning to build in the near future. Okay. So why we use APL? So, okay, I told you we have a long tradition, and then because all our older models are built using Dyalog APL, so we want to preserve the compatibility with the macro model and also these population and employment projections. And also, for example, now we are analyzing several policy proposals for the new pension system. So then APL is quite flexible for modeling various pension rules. And then also, what comes to the results, then it's quite easy to pick the results that we are interested in. Because, well, our simulation generates quite a lot of data, so then we have to choose what we are interested in, because you just can't be interested in everything at once. Okay, so the most of the modules are implemented using Dyalog APL, and, well, some steps with the start data and results can also be used with SAS, and then we need SQAPL and stuff. But the idea is that my modules are as independent as possible. And this is done so that each module is a separate workspace. So what I mean by a module, I mean each box here, these blue boxes are the modules I have in the model. So they're each separate workspaces. And also the links to the other models here are done the same way. So they're also APL workspaces. So this is the only piece of code I have here. So each of my module is implemented as a separate workspace, and the data flows through my model via component files. So first I make a component file out of my start data, then I pass it to my population model. Then what I get out of there is the input for the earnings generation module and so on. And finally, I will have a component file out, and then I can collect the results from there. And the only links between these separate modules are implemented using these component files, so that I don't have any other cross-links, so there that I can easily maintain the whole model, because it's actually quite complex. So to avoid all the cross-links that you maybe don't even know. So if I have separate workspaces, then I can't make any cross-links by accident. That's the main point here. So I'm trying to make my life a bit easier. So these component files I have, they are quite big. So typically I simulate 77 years, and after adding all these new people there, I will have like 500,000 individuals in my data. So, well, and for each individual I have roughly 20 attributes each year. So I have quite a lot of numbers, and the size of such a component file can easily be 5 gigabytes. And, well, when you have several of these files, then it's quite a lot of well, it will be quite a lot altogether. So something else on this implementation. So each module here can be run separately. So if you have before made some start data for the corresponding module, then you can only run one module at a time. And actually, that's what we've been doing. So if you only change, say, some pension rules, so you don't necessarily have to simulate again who will die in the simulation run, but you just compute the pensions again. And each module run takes, well, 10 to 40 minutes with my laptop. I'm not saying that this is optimized in any level. We have done some optimization, but I'm sure that there is lots of things to do. But it works anyway. And well, if you count all these together, so if you run from the start to the very end, it will take around 1.5 hours to run the whole model at once. So this Dyalog APL14, it's quite useful for us. So like compressing the components. So I tried for these component files, and it goes, this 5 gigabytes goes to less than a giga. So it's 16% of the original value size, and it doesn't really take any time for me. Then, of course, the optimization and parallelization, they are like, well, tailor-made things for us. Not literally, but I think they are very useful for us. But unfortunately, we haven't had too much time to complete this transition yet. But once we have the time, I'm sure this is quite high in our priority list to complete this transition. So then I will show some examples of results. So for example, I don't know if you know what is replacement rate, but it's like when you retire, what is your pension compared to your final earnings. And here you have the median and then upper quartile and lower quartile and something like this. So you, in the beginning, these will go down, but then it will be quite stable in the long run. But if you see how the pension distribution will go, for males, it's these blue lines. For females, these red dotted lines. And actually, the purchasing power of the pensions will go up, even though the replacements will stabilize. So in the future, we will develop again our model. We will complete this transition. We will do some optimization on the code, and then we have some of these extensions. I had something in the picture there, and then we also have some other in mind. But I'm sure there will be lots of things to do. But well, thanks for your attention.
I know you said you hadn't implemented the parallelization as of yet, but
yes.
I would imagine that you already have an expectation in terms of how much further you can speed up the running of the entire model if you use the parallel processing?
Well, I think that it could go to the half of the present running time easily. There are natural points where you can parallelize because you have such a lot of data, so it's quite easy to find the points. I just was trying to do it, and I had some like practical problems. So, but I'm pretty sure that I'm going to make it quite soon.
Did you see any performance improvements when you went from 12.1 to 14? You mentioned the component files are smaller because of compression. But
It's roughly 20%, I would say.
Just out of the box, switching from 12.1 to 14?
Yeah, well, it depends on the module, but I don't remember the exact amounts, but it was quite a lot. So something you can really observe.
Yes, a question. You mentioned a bit about it, but what is it used for actually? Who is using the result of these simulations?
Okay, yeah. Our main purpose is the decision makers. Like there is this, I mentioned there is this major pension reform going on. Actually it's going on right now. So they are interested in how the pension distributions look like. That's the main point. And then also like the general public are interested how their pension will behave in the future. So it's like several different audiences.
When you're considering changes to the model,
Yes.
Is it one of your criteria to make sure that the model then, when testing, you take past data and it predicts to be true? In other words, last 2 years ago, apply the model and you predict this year?
Yeah, of course, it's very difficult to verify the model very easily because we are simulating like several tens of years ahead. So if you observe like 5 years, well, it's not very much yet, and yeah. So it's difficult, but it can be done to some extent. But well, I didn't mention we started developing this model last year, so we haven't been able to check how we are doing really.
I was a bit. I found a bit strange that in
Yes.
the first graph you show,
Yeah.
the distance between the optimistic and pessimistic possibilities is not increasing a lot. It looks like that the model have the same affidability for
Yeah.
near dates and 77 years
Yeah.
in the future.
That's true, but there is like a feedback. So if the GDP doesn't grow as fast as expected in the beginning, it will appear here, but then you will accrue less pensions. So in the future also the pensions will be smaller. So it comes from there because it's like related to your GDP. So.
Okay, then I think we'll finish at that point. Thank you very much, Heikki, for a insight into your pensions work.